In this last, very short unit, we're going to discuss the rest of the image sensing pipeline, which is what happens with the light after it has passed through the lens and arrived at the image plane until it is stored in a digital format such that we can use it for computer vision applications, for instance. Here's a simple schematic of the image sensing pipeline that at a very high level can be divided into 3 stages. The first is the physical light transport stage in the camera lens and the body, comprising the optics, the aperture, and the shutter. Then there is a photo measurement stage and conversion on the sensor chip that measures the photons, adjusts their intensity, and converts them into a digital format. That's also sometimes called the raw image. And then there's in most digital cameras, there's another digital image signal processing and image compressing stage where the images are denoised and sharpened, the colors are converted, a white balance is adjusted, and they are compressed into a representation, for instance, using JPEG, that is more memory efficient to store. So once the light has passed through the lens and just before it hits the image sensor, there's typically a shutter. And what we see here is a focal plane shutter of a camera. And most digital cameras today use a combination of a mechanical shutter and an electronic shutter for various reasons. Now the shutter speed, this is a little curtain here that opens and closes very quickly. It's open only it typically can be opened from one side and then closes with another shutter, with another curtain from the other side. And it is open only for a fraction of time, for maybe 1/100th or 1/1000th of a second, 1 millisecond. And so the time that you open the shutter controls how much light reaches the sensor. This is called also the exposure time. And it also determines if an image appears over or underexposed. If your shutter is open too long, then your image will be overexposed. There will be completely bright spots, completely white spots where you cannot recognize anything anymore. If it's underexposed, it will appear too dark. If you are taking a picture in a dark scene, then you have to open the shutter for a long time, maybe a second or so. And then you have to hold the camera very still, because if you move the camera during the exposure time, you will have blur in the image. So the shutter time also determines the blur and the noise behavior. If you have a very dark scene and you move the camera so you want to keep the shutter time short, then you don't suffer from blur, but you increase the noise because there's now less photons per pixel that are measured, and the noise of the measurement process is amplified. How is the measurement process actually working? There's two main principles, CCD and the CMOS chips. And in the past, CCD chips were the primary chips that delivered high quality, but today most of the sensors actually use CMOS sensors. The way they work, the way they measure light, both of them, of course, transform photons to electrons, but the way they work is slightly different. In CCDs, CCDs move charge from pixel to pixel here, and then convert this into voltage at the output node, while CMOS images convert charge to voltage inside each pixel and don't have to carry charge over multiple sites. And this has some advantages and some disadvantages, but today the advantages overweigh. And then this little orange block that you see here is the gain. This is basically how this charge is amplified before converting it to an electronic signal. Now, larger chips so-called full frame sensors, for example, that are the size of a classical film format, 35 millimeters, are more photosensitive because each pixel is larger, so they produce less noise. Now, in order to take pictures of color, we have to measure color. And color is measured by putting a little filter of color on top of each pixel. But because each pixel can only measure one single color, you have to arrange now these pixels in a certain pattern, and it's called a color array, where each pixel in a color array is responsive only to a particular color. And the most commonly known pattern is the so-called Bayer RGB pattern that you see here, where there is a green, red, blue, green pattern that is replicated throughout the entire sensor array. And because you're measuring pixel colors, or the color, only one single color, red, green, or blue at a particular pixel, you need to interpolate the missing pixels. And this is illustrated here on the right. So if you, for instance, measure green, then you have to interpolate red and blue from the neighbors. And this process is called demosaicing. And there's various algorithms for demosaicing, and the choice of algorithm depends on how much time you have and how the quality of the result should be. You want to avoid some of the artifacts that simple demosaicing algorithms typically make. Here's another illustration where you can see the little photosensitive elements of a CMOS chip, and you can see the filters that are put on top of these chips and that let only certain light pass. Now, why is there more green pixels in this array than there is red or blue pixel? The reason for this is that we are more sensitive to green colors, and that's why we put more of the green pixels onto this array. Now, these individual pixels, of course, don't just record a single wavelength, but they record an entire range of the green spectrum, for instance. And how that looks like depends really on the particular sensor that you're using. The so-called spectral response curve of each pixel or each color is typically provided by the camera manufacturer. Here, what you can see is one of the cameras that we are using in our research, and on the right you can see a screenshot from the manual of that camera, and you can see how different colors correspond to different wavelengths. And you can see that this is not even monotonic. It has like the green curve for example corresponds to green, but also a little bit outside of the green spectrum. Here on the bottom you can see the wavelengths. But each of these pixels then basically what it does is it integrates the light spectrum over this spectral response curve. So what we're getting is an integral over the light spectrum according to the spectral sensitivity of the camera, integrated over all wavelengths that are coming in. Now, in order to store and to represent color images, different color spaces are typically used based on the purpose of what we want to do with these images. So a classical RGB representation is shown here. For printing, sometimes different color spaces are needed, or also for image processing. There is, for instance, the LAB color space or the HSV color space. The HSV color space is separating not into red, green, and blue channels, but is separating into hue, saturation, and value. And you can see from this that the hue component is factorized out. So here we have basically the reflectivity or the color, and here we have the saturation, and here we have basically the overall intensity. So depending on what computer vision application you have in mind, some of these color spaces might be more suitable than others. Now, in order to store these RGB or other color spaced images onto disk, we have to discretize the values. We have to discretize them in a clever way. And because humans are more sensitive to intensity differences in darker regions, what we typically do is use so-called gamma compression. It's beneficial to non-linearly transform the intensities or colors such that prior to discretization, and to undo this transformation during loading such that the intensity differences in the darker regions are kept intact despite quantizing the colors to maybe 8 bits in which we want to store this on the disk. And then another thing that typically happens is we compress the images, because storing images as raw images is still quite expensive. So we typically compress the images in something like a JPEG format that you're all familiar with. Typically luminance is compressed with higher fidelity than chrominance, just because humans are more sensitive to luminance. And in the classical compression techniques like JPEG, often an 8x8 patch-based discrete cosine or wavelet transform is used. And these transforms are basically an approximation to PCA of these little patches of natural images. And then the coefficients of this discrete cosine transform, so here on the left you can see examples of these discrete cosine transforms. Once you have converted them, these patches, these 8x8 patches, into the coefficients so that they can be optimally reconstructed with this cosine transform, then these coefficients can be stored efficiently using Huffman codes and give you a huge gain in terms of memory efficiency when you store this to disk. Here on the right, you can see how different levels of compression, different sizes of these codes lead to different discretization or compression artifacts. So you see the typical JPEG artifacts for very strong compression here on the right-hand side. And more recently, deep neural networks have also been explored for improving compression algorithms. And it turns out that you can actually be quite a bit better, maybe unsurprisingly, than this very simple 8x8 patch discrete cosine transform compression. That's all for today.